Hi everyone, this is Mrs. Olson. This is lesson 3 of Unit 4, Quadratic Application Problems. Your goal for today is to use the different forms of a quadratic equation to represent and solve application problems, otherwise known as word problems. You're going to encounter two types, usually, of quadratic problems. Their trajectory, meaning something goes up in the air, and then because of gravity it comes back down, and that makes a parabolic shape. And there's also area model type problems, which we'll do today. Example 1, this is a very typical application problem for quadratics. So we have a model rocket that's launched from the roof of a 2-story building. Its flight path is modeled by this equation, where h of t is the height of the rocket above the ground in feet, and t is the time after the launch in seconds. Some typical questions that we might be asked: when does the rocket reach its maximum height? What is the rocket's maximum height? And also, when does the rocket hit the ground? So for every problem that you do, we want you to sketch out a possible graph that would represent the problem that you're given. So I'm going to make a set of axes where my y-axis is kind of to the left and my x-axis is low. Most trajectory type problems have that upside down parabola look. Along your y-axis, which for us is representing the height, which was in feet, we have the y-intercept. So remember that if it is in standard form, which this equation is in standard form, the c value, your constant, is the initial height, right? That is the y-intercept. So we do know, and I'm just going to put 24 here randomly kind of on here. We do know that this starts at 24 and it's being launched upwards, and then because of gravity comes back down. So we're just going to do a rough sketch, something like that. So you can see the parabola, it's upside down. We know also from the equation that it's supposed to be upside down because our a value is negative. By the way, this negative 16 is very typical. That's representing the pull of gravity on an object. The middle term is your initial velocity. If you're dealing with meters, this first number would not be negative 16, but negative 4.9. It can change because you might take out a common factor or whatever, but that's very typical for these type of problems. Now, what I didn't show is this parabola does, kind of keep going, and we want to label the vertex and the different intercepts. All right, so here's the vertex, and the intercepts would be our t-intercepts, or like our x-intercepts, but we have time. And I'll label it t sub 1 and t sub 2. And again, t is time in seconds. All right, our vertex, this is what we would want to look at for the first two questions of when, right? When is it going to reach the highest point? That is going to tell us that. And the other question that this point will answer for us is how high. So we have our x and our y, or you could say our t and our h values, and those will represent these two here. Oops, sorry, it's hard for me to talk and write at the same time. There we go. So the vertex will answer those two. This point down here answers that third question: when does the rocket hit the ground? When does it hit the ground? And this might be a ball that's thrown, it might be the water balloon that eventually hits the ground, or some other projectile that will go up and then come back down. All right, so that's our picture. Let's actually do the work to solve these. When does the rocket reach its maximum height? So how do I find the vertex? Because it's in standard form, let's just review here. If you have an equation in standard form, like this, ax squared plus bx plus c, then we know that we can find the x-coordinate of the vertex by taking the opposite of b over 2a. Now, in this particular problem, x is really t for time, and we have, that'll be the opposite of 56 over 2 times negative 16. All right, I'm going to do a little math here off to the side. We have 56 over 32, and that's going to be 1.75 seconds. So my coordinate up here, we know that the x-coordinate or the t-coordinate is 1.75. What is the rocket's maximum height? Well, that will be the y-coordinate of the vertex. So I'm going to take what I got in the first problem, and I am going to plug that back in to the equation, right? I'm going to plug it back in. So I'm going to take h of 1.75, and I'm going to put everywhere I saw t, put 1.75. And I can use my calculator after that and solve, and we'll get 73. And the unit is feet. Notice I did put the units with my answers because you are dealing with a context. You do want to put your units with your answer. So that's our vertex. Reaches its highest point at 1.75 seconds, and that highest point is 73 feet above the ground. This last question about when does the rocket hit the ground, those are our x-intercepts, or in this case our t-intercepts. So those are our solutions, our zeros, our roots. That's what we spent all of Unit 3 doing, solving. So if we look at our equation, I have some big numbers there. I want to set that equation equal to 0 and use one of the many methods to solve. Quadratic formula, completing the square, factoring. Now I do have a common factor here of -8 that I am going to divide everything by -8. That is going to make my numbers a little bit smaller, and if I do use the quadratic formula, it'll be easier to plug those in. All right, so I'm going to plug those into the quadratic formula. Instead of x, we have a t. I'm going to take the opposite of b, plus or minus, and so on. This is a -7, excuse me. All over 2a, and a was 2. That's supposed to be minus sign right there. When you simplify this, you get a 73 under the radical. And because, again, there is a context to the problem, we're going to go ahead and put these in our calculator and see what they're equal to. The first value I get is about 3.89, and the second value I get is about -0.39. Now, in the context of the situation, that -0.39 would be back here, back in time. That's my negative value. That's before the rocket was ever launched. So that really doesn't make sense in the context of the problem. So I only want the 3.89 value when the rocket will hit the ground. So I am going to keep this value, but I am going to disregard the second one, again, because in the context of the problem, it doesn't really make sense. All right, we're going to do a few more. Example 2. The path of a place-kicked football can be modeled by the function, and we have that equation where x is the horizontal distance in yards and y is the corresponding height in yards. How far is the football kicked? What is the football's maximum height? All right, again, I recommend that you draw a picture. You might also want to underline some important information. And I always underline the question. And in this case, we have two. How far is it kicked? And what's the maximum height? All right, so I'm going to draw a picture. Again, the y-axis off to the left and the x-axis kind of low. Now in this case, we have x is our distance in yards, and our y-axis is our height, also in yards. Now let's look at our equation. Notice this is an intercept form. You might not recognize that, but the x right here, you could write as x minus 0, and then we have our other intercept that's represented in that binomial there. So this means that our x-intercepts are 0, 0, and 46, 0. So over here at the origin, 0, 0, and then over here, 46. And our parabola will go up and then back down. It is a negative a value in the front, right? So we do know that this is an upside down, opens down parabola. So there's our rough sketch. Our vertex here would answer our second question, what's the football's maximum height? So we're going to need to find that. And then how far is the football kicked? Well, since we can answer the first question right away, since this is the point 0, 0, and this is the point over here 46, 0, we know that the distance that it was kicked, total distance, is 46 yards. So for the first question, it was kicked 46 yards. For the second question, because we're given intercept form and we want to find the vertex, we are going to use the average of our intercepts, p plus q divided by 2, and then plug that back in. All right, so we have, well, what is p and q? It was 0 and 46, so we get 23 for our x value here. We're going to plug that back into the equation. Everywhere there's an x. And solve. Okay, so we're going to get here, after you multiply that all out, you get 13.754 yards. And that is the answer to our second question. What is the football's maximum height? 13.75 yards. Okay. The next one is one of the area model problems. So the first two were trajectory and this one's an area. So just to review, when you're finding the area of a rectangle, you're going to use length times width. And all of the area problems will be using that formula. Example 3, Mrs. Olson's garden currently has dimensions 6 feet by 4 feet. Mrs. Olson wants to double the area by extending each side of the garden by the same amount. What will the new dimensions be if the garden is extended the same amount in each direction? Also, the doubling the area is an important piece of information. So let's sketch it out. The current dimensions are 6 by 4. And feet, you put a little tick mark there that represents feet. That means the area of this current garden is 24 feet squared. If we want to double the area, that means we want it to be 48. Double that amount, we'll get 48 feet squared. All right, let's also sketch a diagram with the new dimensions being added. So the original was 4 by 6, and we're extending it by the same amount. I'm going to call that amount x. So I'm extending each dimension by the same amount x. So this is what our new garden looks like. The new dimensions here are 6 plus x, and over here 4 plus x. So our area equals length times width. Our area, we want it to be 48, and our length and width, and it doesn't really matter which one's length or width. And it also doesn't matter that I have the 6 and the 4 in front of the x's. That's okay, you can switch them around. But we are going to FOIL here, and we're going to get, when you FOIL that all out, and I'll go ahead and put it in descending order, looks like this. All right, so if we want to solve for this, we have to have everything equal to 0 if we're going to use quadratic formula or factor, or we could use completing the square. Any of those methods would be fine. Choose the one you like best. I'm just going to go ahead and subtract the 48 and see if it'll factor. If not, I'll use the quadratic formula. And that would be a negative 24. So I think this will factor. I know that 12 and 2 have a product of 24 and a difference of 10. So this is going to be x plus 12 and x minus 2. Again, choose your own method that you like. You can always use quadratic formula if that's what you're comfortable with. Set these equal to 0. X equals negative 12. And x equals 2. Now a negative value in this case would not really make sense. If I plug negative 12 in there, then my total dimensions are negative numbers. So that's not going to work. Again, in the context of the problem, that one doesn't work. But the x equals 2 does work. So we are going to extend each direction by 2 feet. And that's our answer. Okay, so I'm going to end this here and then do another video for 2 more problems. Try them first, and then you can watch the video